Okay, I will start. Donc si on m'entend plus, au fond, vous me faites signe d'une manière ou d'une autre. Ok, merci. There was some technical problem with the microphone. So what I haven't done in the first lecture is to explain to you what the goal of this lecture is. So it's better late than never. So the idea is to have a correspondence between on one hand Lagrangian submanifolds, and in our situation it will be in some cotangent bundle of n. And on the other hand, I will have sheaves. So this will be ordinary sheaves, not holomorphic or any special property. Well, actually, they will have some property of what's called being constructible, but it's not relevant for the moment. But certainly, they are not holomorphic. Sheaves let's say on the product of n times r, or at least on some simple manifold which is constructed starting from n. And here, to make things simpler, even though you can try to extend that to the general case, you're looking at exact Lagrangian submanifolds, and so on this other side you have sheaves. And in fact, this is going to be, or should be, a correspondence of categories. Okay, so what are the categories here? Well, here, let's call FD the Fukaya-Donaldson category. So what are the objects of this Donaldson-Fukaya category? Well, they're exactly the exact Lagrangians. Exact Lagrangian, I think I said that last time. It's a Lagrangian such that the Liouville form is exact on L and not only closed. So exact means is the differential of some form F. And the morphism here, and I will explain in a second. So you have two Lagrangians, L1 and L2, and the set of morphism is going to be a vector space, and this vector space is the Floer homology of L1 and L2. And for the moment, you don't know what's the Floer homology of L1 and L2. You only know what is the Floer homology for a Hamiltonian, associated to a Hamiltonian flow. So I will explain what this Floer homology is. Okay. And on this side here, well, you have the category where the objects of this, let's say it's called SH of n times r, these are sheaves over n times r. And well, it's a little bit more complicated, but the morphism between two sheaves well, they will be defined later. They are essentially the morphism between sheaves. Yes, this sounds very stupid when you say what's the category of vector spaces. Well, the objects are the vector spaces and the morphism are morphisms of vector spaces, of course. Okay, in fact, here you have to make a small modification because of this R factor, but I will go into that a little bit later. So you could say, okay, I have this correspondence. Why is it nice to have such a correspondence? Well, for one thing, sheaves come in many ways in mathematics, and so this means that you're going to somehow translate problem about sheaves to problem about Lagrangian submanifolds. And on the other hand, sheaves are very flexible tools. I mean, you can do many things with sheaves. And so it's also very convenient to study Lagrangian submanifolds using sheaves, because Lagrangian submanifolds are sort of very rigid object. I mean, in particular, when you're talking about embedded Lagrangian submanifolds, I mean, it's not something that is very, very convenient to deal with. So let me give some examples of applications for the moment. They are essentially two known theorems, and I refer you to, well, first there are some lecture notes on my web page. Which corresponds to some lectures I gave at Columbia, so Eilenberg. And then once you download these, there are a number of references, and some of the references are as follows. One is a paper by Guillermou, Kashiwara and Schapira. Another is a paper by Tamarkin. And another is a paper by Nadler. And another one still is a paper by Fukaya, Seidel, and Smith. So all these are somehow relevant to what I'm going to discuss today. Well, in the coming lectures. Okay. So what is an example of maybe the most spectacular application of this kind of correspondence is the following. Consider L in T star n to be an exact Lagrangian. Well, there's a conjecture by Arnold. It's hard to say the Arnold conjecture because there are many of them. So this is a conjecture of Arnold, which says that there exists some Hamiltonian flow such that L is the image of the zero section by this Hamiltonian isotopy. So this is an extremely strong conjecture. It tells you that the only way to construct an exact Lagrangian in T star n, I should have said that n is compact here, well, from the beginning. The only way you can get an exact Lagrangian submanifold is to start from the obvious one, which is the zero section, and then apply a continuous deformation by Hamiltonian isotopy, which of course is going to give you exact Lagrangian, and in this way you get everything. So you can imagine that because this is a very simple statement and very strong, it's extremely hard. I mean, for the moment, it's completely out of reach. People don't even have the slightest idea of how you could prove that. I mean, I give you an exact Lagrangian, and what you have to do, you would have to produce an isotopy which brings it back to the zero section. It's not even completely trivial to do that in one dimension. I mean, you can sort of do it by hand in one dimension, but as soon as you go to two dimension, you have no idea how you should deform this Lagrangian, and there's no particular way of deforming a Lagrangian. I mean, there's nothing like you could imagine something like a Ricci flow or something like that, but so far nothing like that exists. So of course, I mean, if you cannot prove a strong result, you sort of try to settle for a weaker result, and you try to see, well, what are consequences of this statement which you would like to prove. So one obvious consequence of the conjecture So we expect the following, which is a theorem. So the theorem is due to Fukaya, Seidel, Smith in the simply connected case. And then there's the generalization by Mohammed Abu Zaid, and uses also some result by Thomas Cragg. And this theorem says that if L be an exact Lagrangian, and all these are compact, okay, of course, in T star n, then the projection from L to n is a homotopy equivalence. Well, why is this trivial in this situation here? Well, obviously, T star n is homotopy equivalent to n itself by just contracting the fiber. Okay? So it's enough to prove that the inclusion from L to T star n is a homotopy equivalence. But the inclusion of the zero section is obviously a homotopy equivalence, and then you apply an isotopy. So this remains a homotopy equivalence, clearly. So if you know how to prove this, then this is a sort of trivial corollary. Okay? But if you don't know how to prove this, this is actually pretty hard. And you can see it's a first step in this direction. However, it's clear that the staircase doesn't go any further. I mean, you can climb a first step, but there's no second step a priori. Once you prove this, you don't have the impression that you got closer to this. I mean, formally you get a consequence of this, but it doesn't give you any hint on how you're going to prove this using that. Okay? Yes, all the manifolds here are compact. I mean, all manifolds that can be compact are compact here. I mean, I don't assume R is compact or T star n is compact, but all the other ones are compact. Okay? So L, N, everything here. So here, these are exact and compact. Okay. And this follows from this correspondence. When you translate, you can translate this problem to a problem about sheaves, and then you apply some sheaf machinery, and I will explain that in a while, and then you actually do get this result. Okay. So I'm probably not going to get to the proof of this statement. I will just get to some weaker statement like proving the Arnold conjecture, which says that L and the zero section have intersection point. Okay, so the classical conjecture only says that L, well, this is even the weak form, but so L intersects the zero section somewhere, and actually in a certain number of points, but that's irrelevant. Okay. Okay, any questions so far? Okay. So I will start with well, I will say that later. I will start with something which is both a sort of baby model of this right-hand side here. So I'm starting with an exact Lagrangian, and I'm trying to describe a sheaf. So instead of describing the sheaf, I will describe what are called generating functions for the Lagrangians. And so historically, this came before and was sort of used as a baby version here. And also, there are a number of reasons to do that. First, that once you understand how this works, you understand much better how the sheaf part works. That's one point. The second point is that when you prove actually some theorems about the sheaves, you actually, it's actually much easier if you use some generating function technique for that at some point. Okay. So these are two reasons for doing that. And the third one I would say is that when you make this construction from Lagrangian to sheaf, you somehow mimic, in a certain way, this construction of generating function. So there's really a number of reasons to do that. So the idea is the following. So as I mentioned last time, if L is an exact Lagrangian in T star n, and if L is a graph, then you know how to describe L. Well, L is of the form L sub f, which is the set of pair x df over x for x in n. And for some function f, let's say in smooth function from n to r. So if you want to describe exact Lagrangian graph, it's very easy. They are just given by smooth function of n over r. Okay. But now it's clear that if you have, well, assume you're on T star S1. Okay. So this is the zero section here. And then I'm looking at some Lagrangian, exact Lagrangian here. Well, there's no reason why this should be a graph. So the question is, how do you describe more general Lagrangians? Well, the idea is instead of having one function, you somehow have families of functions. So let S be a function from n times rk to r, where k is some large integer. So I usually write like this to say k is very large, but then some analyst told me, no, every number is large compared to 0. You should put k greater than 1. I don't know. Anyway, you consider sigma s, which is the set of critical points in the fiber. So sigma s is just the set of x and psi in n times rk, such that ds derivative with respect to the fiber psi is 0. And I want to assume that this sigma s is a smooth submanifold. And for this, I need to assume transversality, which means that I have to assume that the map from x psi to ds over d psi has 0 as a regular value. So I assume 0 is a regular value of x psi ds over d psi of x and psi. Okay, so what happens next? Well, next, you look at the map IS from sigma s to T star n, which sends x psi, the pair x psi, to the pair x ds over dx of x and psi. And my claim is that IS is a Lagrangian immersion. So why is it Lagrangian? Well, look at the pullback of the form PDQ. The pullback of the form PDQ is just ds over dx here of x psi dx. But because I'm at a point where ds over d psi is 0, this is the same. Sounds stupid, but it's the same as ds over dx dx plus ds over d psi d psi. And this is just the differential of s restricted to sigma s. So you see that it's not only a Lagrangian, it's also exact. And the second point is why is it an immersion? Well, this is because what we're doing actually follows from automatic transversality. In fact, what this construction is, it's just taking the reduction of the graph of the S, IS of sigma S, is the reduction of the graph of ds, so the set of x psi ds over dx x psi ds over d psi x psi. So let's denote this coordinate by x, psi, p, and eta here. So I'm doing the reduction by eta equals 0. So this is in n, this is in Rk, this is in Tx star n, and this is in Rk dual. Okay, these are dual coordinates. So I look at the coisotropic submanifold eta equals 0. Okay. Now the kernel is exactly given by the direction of psi, so I'm going to forget psi. So I'm intersecting here with ds over d psi equals 0. That's what it means taking eta equals 0. Okay, it means putting ds over d psi to be 0. And then I forget this coordinate psi, so what is left is x and ds over dx, okay, at the points where ds over d psi is 0. So this is just the symplectic reduction by eta equals 0. And then I could even have saved the first part, okay, because this graph is, of course, the graph of the differential of s. It's Lagrangian. And I'm doing the symplectic reduction of this by eta equals 0. If I have transversality to eta equals 0, which is the assumption I have here, then the projection is an immersion, and I get an immersed Lagrangian. Okay. Any questions so far? Another remark why this point of view can be relevant is the following. If Ls, which I use as a notation for the image of sigma S, is embedded, then the intersection of Ls with the 0 section is in 1-to-1 correspondence to the critical points of S. So why is that? Well, a point in Ls intersection the 0 section must correspond first to a point of Ls. So it must be a point where the derivative of S with respect to psi vanishes. And then I want this point here, where is it? Here, to be in the 0 section, which means I want ds over dx to be 0. So I want both ds over dx and ds over d psi to be 0, which means that x psi is a critical point of the function S. What is wrong? Well, if it's immersed, you could have 2 points which correspond. See, I mean, it's just nothing is wrong except that you could have this. And then the same point corresponds to 2 values. That was the only reason why. But it's, if you count with multiplicity, then you indeed have 1-to-1 correspondence. So you could say, well, the story is over now. You just have to show that some Lagrangian have a generating function, and then you find critical points of S, and that's it. You get intersection point of L with the zero section. That's going to be easy. So the question is, does there exist an S for each L? So that's the question. And the answer is almost yes. There is some topological obstruction. This is a result by Emmanuel Giroux. Rather old result. And the answer is yes, with some easy, I would say, obvious vanishing of topological obstructions. So there's a topological obstruction which I forgot right now to have a generating function, but once this topological obstruction vanishes, you know that there's a generating function. Okay. So that sounds like good news. Now comes the bad news. The bad news is that I said all the manifolds which can be compact are compact, but R is not compact, of course. So that's the bad news. So you know that a function on a compact manifold always have a critical point, but a function on n times Rk does not necessarily have a critical point. That's the bad news. So a function from on n to Rk to R does not always have critical points. Okay, so once you said that, well, there are two ways out. One is to throw this whole idea to the trash bin and say, let's try to find some other way. And the other one is to try to say, well, okay, some of these functions don't have a critical point, but some do, and let's try to find if there's a reasonable class of function which have a critical point. Okay. So the question is, can one find a reasonable class of S generating function having critical points, so which are guaranteed to have some critical point, at least one, let's say. And of course, then it's a sort of, the problem is a problem of balance. I mean, you imposing a condition, you tend to impose a very strong condition. On the other hand, if you impose a very strong condition to the class of admissible S, you reduce the chances that any L will have such a generating function. Okay. So the real skill is to find what's the proper balance. And the proper balance is as follows. So the generating function S is said to be quadratic at infinity. If there exists a non-degenerate quadratic form Q of psi such that S of x and psi coincides with Q for psi is sufficiently large. So at infinity in psi, remember there's no infinity in n because n is compact, at infinity in psi, S coincides with a non-degenerate quadratic form, and that's my only requirement, and the notation is, just for short, is GFQI for generating function quadratic at infinity, which is notation I will use from now. Now this looks quite restrictive. It's not as bad as it looks in a way, because it's an asymptotic condition. So you have the impression it's very strong to assume that S is exactly like a quadratic form at infinity. My claim is the following, is that if S just looks vaguely like a quadratic, non-degenerate quadratic form at infinity, then you can deform it to be precisely a quadratic form. And so you can actually you don't see a difference. So let S be a generating function for L such that for some non-degenerate Q, so quadratic form, we have first the gradient of S minus the gradient of Q in the C0 norm is bounded, and second, the sup of S minus Q over a ball of radius R grows at most linearly. Then L has a generating function quadratic at infinity S tilde. So in particular, there are lots of operations which are much easier with generating function which satisfy this. For instance, if you want to add two generating functions with different fibers, okay. So you want to add S of x and psi and S of x and eta, it's not going to satisfy this strong property, but it's trivially going to satisfy this property here. And so things are much easier to handle. So I don't want to give the I just want to give the hint of the proof here. It's just by gluing. So you just take a function here, which I will call rho. Which is 1 up to A. So rho is 1, rho of f is 1 for S less than A. Rho is 0 for S greater than B. And rho prime is negative and has derivative at least epsilon. If you take A and B large enough, you can always do that. And then you take S tilde of x and psi to be, is it 1 minus? Well, I'd better look it up. Is rho of the modulus of psi, S of x and psi, plus 1 minus rho of modulus of psi, Q of psi. And then you have to be a little bit careful on how you choose the parameters. Okay. And it's very important, I should stress this, that the quadratic form here is non-degenerate. The quadratic form is degenerate, you cannot do anything. The quadratic form is non-degenerate, everything works. Okay. And so you write this function as tilde, and it's easy to see that if you're looking at the critical points in the direction of psi, they're actually going to be the same. So then you check that ds tilde over d psi is 0 if and only if ds over d psi of x and psi is 0, just because this condition will imply that modulus of psi is small enough. I mean, or not too large. It remains. So you have to play with a and b and epsilon. Okay, and there's essentially no difficulty here. Okay. So the main theorem now is the one that was somehow promised to you. Okay, it says, well, I'm restricting the class of generating functions, but I still want to have sufficiently many Lagrangian. So this is a theorem which is due to Sikora and Lodenbach, and says that if L is the image of the zero section by a Hamiltonian isotopy, then L has a generating function quadratic at infinity. And the proof I'm going to explain is actually due to Marco Brunella, who unfortunately passed away some months ago. And not many people maybe know that before working in complex variable, he had actually worked in symplectic geometry. And he had this very beautiful proof of this theorem in particular that was many years ago. So the idea is somehow to do it by induction. And by doing it by induction, I mean, assume you have L, which has a generating function quadratic at infinity, apply a Hamiltonian isotopy, and now I can assume that the Hamiltonian isotopy is small. So I apply a small Hamiltonian isotopy, then phi of L also has. So it's enough to prove that for phi close to the identity, if L has a generating function quadratic at infinity, then phi of L has also a generating function quadratic at infinity. Well, why is that? Well, because if you have phi is phi 1, you can always write phi as the product of phi I plus 1 over n, phi I over n minus 1. This one is going to be C1 small for n large. Okay. And so you wrote phi as a composition of small maps, and then of course, if you start from the zero section, you know it has a generating function quadratic at infinity, and then all the image, by composing all the image, will have a generating function quadratic at infinity. Of course, for 0 n, S is 0, identically 0 is a generating function, needless to say. Okay, so it's enough to do it for. Sorry? Yes, because that's because you were not trained in the Bourbaki category. Any function on a zero-dimensional vector space is quadratic. Okay, sorry for that. Well, if you don't like that, just take norm of psi square. Okay. Okay, so what you have to do is to prove this for small maps. Okay. And now I'm going to consider special special maps which are called, well, sometimes they are called twist maps, which are defined as follows. So first I'm going to assume that N is a Euclidean space. So it's non-compact now. Now I'm going to look at a function h of q1 and q2. And to this function, I'm going to associate maybe some symplectic map phi h. And the symplectic map phi h is defined as follows. While phi h of q1 p1 is equal to q2 p2, if and only if p1 is dh over dq1 of q1 q2, p2 is minus dh over dq2 of q1 and q2. So where does this sort of strange thing comes out from? Well, it comes out from looking at T star n times T star n here. So here you have q1, p1. Here you have q2, p2. You have this projection here, which is the projection over q1, q2. Let's put the opposite symplectic structure on the second factor here. Okay. Now the fibers here are, of course, Lagrangian fibers. Okay. And if I have a symplectic map, so if phi is symplectic, I have the graph of phi which sits in T star n times T star n, or T star n times T star n bar, and is Lagrangian. So remember we said the last time that saying that the map is symplectic is the same as saying that its graph is a Lagrangian submanifold. So I have a Lagrangian submanifold in here, okay? And depending on the situation, when I look at the projection here on Q1, Q2, either I have a graph or I have an awful mess. Okay? I mean, I don't know what's going to happen a priori. I mean, I have this map here, and well, it's hard to, let's say this would be the Q1, Q2. I don't know whether this graph is going to be like this, or maybe it's going to be like this. Who knows? Okay? But in some good cases, it could be like this. And in this case, it should be the graph of the differential of a function over the base. Okay? And this is exactly what the function h is. Okay? So if I have a phi such that when I look at the Lagrangian, at its graph as a Lagrangian in T star n times T star n bar, I get a graph over Q1, Q2, then it's given by the differential of a function h, and this is the function h. And also it happens sometimes that if I start with the function h, and I look at the graph here, well, this may be or may not be the graph of a diffeomorphism phi. It's going to be certainly the graph of a Lagrangian correspondence, but this correspondence may or may not be a map. I don't know. Okay? But in some cases, this happens. Okay? And in fact, this is good enough. What's important is to notice that whatever the situation, if I'm in the good situation, the condition is going to be an open condition. Okay? So if I have a map phi which is of this type described by h, and if I move a little bit the map phi, then I will have another h. Vice versa, if I have an h which corresponds to some phi, if I move a little bit h, let's say at least if I move it a little bit C2, okay, if I make a small C2 deformation, then I will get another diffeomorphism phi, because being a diffeomorphism or being a graph are all open conditions. Okay? So let me give you a trivial example, which is the one I will use. h of q1 and q2 is 1/2 of q1 minus q2 square. And what is the map that you get here? Well, the map is P1 should be dH over dQ1, so it's going to be Q1 minus Q2, and P2 is so minus Q2 minus Q1, so it's going to be Q1 minus Q2 as well. So this you can rewrite as saying that P2 is equal to P1, and Q2 is equal to Q1 minus P1. So this is what's called the twist map. This is a map that sends this vertical here to this map here. Doesn't matter so much what you get. You just get a map phi. Now it's not hard to see, so let's denote this. So this is phi h. So let's call this h0 because this is somehow important. And you can see that phi minus h0 is actually phi h0 minus 1. You just check, and you will see that you get the reverse. And now I have a little bit more, okay, in the sense that if h is close to or let's see if psi is C1 small, then psi composed with phi h0 is of the form phi h for some h. That's this open argument I gave you. Move a little bit. Phi h. So this is equivalent to saying that any such small psi can be written as phi h composed with phi h0 minus 1. I just rewrote the same thing. Okay, no, so now what's the next step? Well, the next step is that if L has a generating function quadratic at infinity S of x and psi, then we get Chekhanov composition formula which tells you that phi h composed with, phi h applied to L has a generating function quadratic at infinity, which is S tilde of x and y and psi, which is h of x and y plus f of s of y and psi. And I hope this is, and this is even correct. It should not depend on h0. Yes, there is there's a dependence on h0, except that h0 is fixed. So I gave you an h0, and then I say from that. Well, you can check the formula. What does it mean that ds tilde over? So what should be clear here is that in all this situation, I have what I call the base variables, the variable which are in N, and the fiber variable, which are the fiber in the Euclidean space. Now, in my situation, it may be a little bit confusing, so I usually separate them by a semicolon here. So x is the base variable, and y, psi are the fiber variables. Okay, which is fine because in my situation, both x and y anyway are in Euclidean space, so this is in a Euclidean space, this is also in a Euclidean space, and the other ones just stay where they are. Okay. So ds over the xi of x y xi is 0. This is equivalent, of course, to ds over the xi of x of y and xi to be 0. And now I have to look at the point x ds tilde over dx of x. Sorry, I missed one condition. There's the other condition is that ds tilde over dy of x y xi should be 0. And this is equivalent to dh over dy of xy plus ds over dy of y xi is equal to 0. And now I have to look at the point x, sorry, ds tilde over dx of x y xi. And this is just x so, sorry, I'm lost for a second. Sorry, no. This is going to be dh over dx here. So it's x dh over dx of x and y. But by definition, this is the image by phi h of y, sorry, and minus dh over dy of xy. That's the definition of the map phi h. And now, this is just phi h of y and ds over dy of y and xi. And so this is exactly a point in phi h of L. Okay, because the points in L are defined as the set of points y ds over dy. Yeah, unfortunately, the important things always end up at the lower end corner of the blackboard. Maybe I will rewrite this on the next one. So as I said, the last line was that x dh over dx of xy is phi h of y minus dh over dy of xy. And this is phi h of y ds over dy of y xi, and this belongs to phi h of L. And it's easy to see that you're actually getting all the points in phi h of L. This way. So now you're. So what's the end of the proof in Rn? Well, start with L, which has a generating function quadratic at infinity. I cheated you a little bit because, of course, S tilde itself is not exactly quadratic at infinity. You have exactly to do the same kind of deformation which I did when I said if you're asymptotically quadratic at infinity, you can deform to something which is exactly quadratic at infinity. Okay, so this is exactly the kind of situation where you have to do this deformation. So L is a generating function quadratic at infinity. Then phi h phi minus h0 of L has a generating function quadratic at infinity, and then phi h composed with phi minus h0 of L has also a generating function quadratic at infinity. And so we proved, because this is psi, small psi, psi of L has generating function quadratic at infinity. So this works in T star Rn, and you should actually be a little bit careful about what happens at infinity in Rn, which I wasn't. Okay. But we can assuming, let's say that L coincides with the zero section at infinity. Okay. And you can check that all these phi h0, and also, sorry, and psi is compact supported. And then you can check that all these phi h and phi h0 preserve this condition of being equal to the zero section at infinity, so nothing happens at infinity, okay, in this situation. And so how do you go to the general case? Well, the general case, now you have n compact in some Euclidean space Rl embedded, and then you take a Riemannian metric, well, take just a standard Riemannian metric on Rl, and this gives you a symplectic embedding of T star n into T star Rl. What does it mean? Well, here you have Q and P. Well, the base point is, of course, going to go to Q. And then P tilde is the only linear form on Rl, which is 0 on the orthogonal of the tangent space to n. Okay? So P is the unique lift of P vanishing on the orthogonal of TQn. And so you get a symplectic embedding, and you get also that this is obtained by symplectic T star n is also the symplectic reduction of n times Rl star. So it's hard to make a picture, but somehow you have Rl here, you have n here, and then you have a kind of foliation here, the isotropic foliation. But of course, you would need more dimension to make a real picture. Okay. And when you divide out by this foliation, you just get the cotangent model of n. On the other hand, the cotangent model of n is itself embedded here. I mean, it's hard to have a somehow realistic picture. Okay. But what you can do is the following. Now let L in T star n be the reduction of some L tilde in T star Rl. And assume L tilde has a generating function quadratic at infinity, S tilde, then L has a generating function quadratic at infinity, S, which is just the restriction of S tilde to n times Rk. So be careful, the Rk here is the set of parameters of the generating function, has nothing to do with the L here. So S tilde is a function which is defined on Rl times Rk. Okay, and when I look at the restriction, I just get the generating function of the reduction. And now it's quite easy to conclude it's enough to prove that for a Hamiltonian flow phi t on t star n, there is an extension phi tilde t to t star r L such that phi tilde of L tilde has, for reduction, phi of L. Essentially, you have to define you have a Hamiltonian which is defined on the QP variable here, and you have to extend it on the QP tilde variable first in a sort of trivial way, okay, by just looking at the projection. And then you have to extend it to the neighborhood, well, more than the neighborhood, but to all possible Q. Not only to Q in N, but to Q in Rn, and then that you do by a cutoff function, so that you check that the Hamiltonian flow is going to preserve this coisotropic subspace. So it's, I mean, it's just, you can write down explicitly what the Hamiltonian is, okay, and then that's not so difficult. And once you've done this, well, you start with the zero section. So end of proof. The zero section, of course, is the reduction of the zero section in RL. Now you apply phi, and then you get a phi tilde, and you know that phi tilde of.
When you expand phi t, then the condition in third line is automatic.
Condition in the third line? This one?
No. So once you define phi tilde t,
yes,
then it's automatic that the phi tilde has for reduction, right? Or not?
yes. If you define it properly, yes. There's a way of defining phi tilde. So given phi tilde, given phi t, there's a way of extending phi tilde t, okay, so that this is automatic indeed. But you have to be a slight. No, no, I don't think so. I think you have to be. No, it doesn't. Well, it doesn't work for any extension because you certainly have to preserve the isotropic foliation. So the phi tilde certainly has to preserve the coisotropic foliation. Okay. Probably, if you guarantee that, then that's enough. Okay, I have the impression. Okay. So let me just explain. What you can do once you have this result. So how does the Arnold conjecture come here? Well, I have L, which is of the form phi 1 of the zero section. So we just proved that it has a generating function quadratic at infinity S. And remember that L intersection with the zero section is in one-to-one correspondence with critical points of S. So what you have to show is that S indeed has critical points. And the way to do that is by applying homological or cohomological min-max which means the following. Well, I will denote by S lambda the set of x psi such that S of x psi is less than lambda. So this is the sub-level set of the function S. And then I will also denote by S infinity to be SC for C very large, S minus infinity to be S minus C for C very large. And my claim is that the cohomology, relative cohomology of S infinity mod S minus infinity is isomorphic to the cohomology of N. Well, actually, with some shift in index. So why is that? Well, because I'm looking at very large levels and very low levels, I can replace S by Q because S is quadratic at infinity. So at infinity, S is like Q. So you can replace S by Q. So what is going to happen? Well, you're going to get the cohomology. What are the sub-level set of the function Q, but consider as a function of x and psi? Well, it doesn't depend on x. Okay, so it's going to be the product of n times Q infinity and n times Q minus infinity. And this is just the cohomology of n. This is Kuhn's theorem by the cohomology of Q infinity mod Q minus infinity. And this is one dimensional. If you have a quadratic form, let's see if I have colored chalk here. So the set Q infinity is going to be the blue set, let's say. And Q minus infinity is the red set. So this is the negative direction. The horizontal is the negative direction. Well, the cohomology of the blue set mod the red set is generated by this cycle. Well, in homology, it's generated by this cycle here, by the negative disk. Okay? And this is one dimensional. So what you get here is that you get in here all the cohomology of n times something which has some degree, and this degree accounts for the shift in index. So what's good of having many cohomology classes here, or at least having a non-zero cohomology class in here, is that you can do min-max. That is, you can look at, decrease this, instead of S infinity, look at S lambda. So now you can do the following. You can do now take alpha in the cohomology of S infinity, S minus infinity, and look at C alpha of S, which is the infimum of the set of lambda, such that alpha is non-zero in the cohomology of S lambda, S minus infinity. So what am I doing there? Well, you have a function S. Just doing most theory. I have a function S here on some manifold. I'm taking some cohomology or homology class. Let's represent it like this here. And I'm trying to lower the level and see if I go too far, this homology class will not be represented anymore. If I get here, for instance, at this level here, well, you see that in here I cannot find a representative of this homology class here. Okay. So if I go, even if I go here, it's not going to be enough. I have to go at least here. So this is going to be the critical value, except that I did it with cohomology, and here it's with homology, but the idea is exactly the same. So you look at the first level where some homology or cohomology class disappears, and by the first Morse lemma, which tells you that the homotopy type of the sublevel set doesn't change unless you cross critical points, this has to be a critical level. Unless you cross critical level, sorry, this has to be a critical level. Okay. And you could say, okay, this is not exactly the framework because the manifold is non-compact, but the fact that the functions are quadratic at infinity sort of takes care of all the difficulties that you could have. So there are no difficulties exactly because the function is quadratic at infinity. So this is a critical value. Of course, it cannot be minus infinity because below a certain level, okay, you know that the function is quadratic, and then this would be like this is 0 anyway. So there's a finite value such that this becomes equal to 0. Okay. So this is a critical value, and the critical value means that there exists critical point for S, and in particular this implies that the intersection of L with the 0 section is non-empty. And if you do more refined critical point theory, what's called Lusternik-Schneermann theory, you find the right number of critical points for this. And another remark I would like to make here, which is quite important, is that C of alpha S depends a priori on the choice of S. I never said, and this is not true, that given a Lagrangian, there's a unique generating function quadratic at infinity. It's actually very easy to construct more of them. Okay. However, the interesting thing is that if you get two cohomology classes, the difference here does not depend on the choice of S, but only on L. So what happens actually is that if you take another generating function S, you're going to shift all these values by the same constant. But if you're looking at the difference between two of them, there's not going to be any difference. So in particular, you can define, it's good, I'm just at the end of the blackboard, so it's time to write something important here. Gamma of L, which is the difference between the top cohomology class, which I will denote as here as N, minus the difference for the point. Okay. And this invariant, so these are called spectral invariants, and are also defined, for instance, in the framework of Floer homology, and have actually been defined also recently in the framework of Sheaf theory. So that's you can begin to see a parallel with the, sorry. Nice music. Huh? So this difference here is actually, it measures the distance between the Lagrangian L and the 0 section, okay, and is an interesting object that you get from this construction. I probably lost my eraser on the way, no? Yeah, it's there. So maybe the best thing to do in the last 15 minutes is to explain the connection with Lagrangian Floer homology. So I think François defined the Floer homology in the case of Hamiltonian flow. You're going to see it's very similar. So let's assume I have L1 and L2 to be Lagrangians. And I could even assume, just to make things easier, you can define it on much more general, but assume they're exact and they are in T star n. You could even assume that one of them is the zero section. It doesn't. So L1 and L2 have some intersection point here. So I define the Floer complex here of L1 and L2. To be the sum, let K be a field. So I plug in a generator for each intersection point. There's also a grading, but I will come to that later. And now I'd want to define, as in the Hamiltonian case, of course, I said I don't define the grading, but I cannot help to writing +1 here because everyone writes +1. And what is the matrix of this map here? So what's delta of x and y, or of ex and ey? Well, let's say I have a point x here, I have a point y here, and I'm going to count the number of holomorphic strips from x to y. So I write algebraic. So the best thing is actually to take k to be z over 2. Then you don't have to count with signs in this case. Otherwise, you have to count with sign. But the algebraic number of holomorphic strips from x to y with boundary in L1 and L2. In other words, this is the set of map U from R to O1 into T star n, such that, so I have a complex, I put a complex structure, and as François explained to you, you can always find a complex structure on T star n. Okay. So the d bar of U equals 0. U of S and 0 is in L1. U of S and 1 is in L2. And the limits as S goes to plus infinity of U of S and T is equal to Y. And the limit as S goes to minus infinity of U as S and T is X. So these are the holomorphic strips starting from here, ending in here. And I should have said that you divide by R because all this, as in the Hamiltonian case, is invariant by translation. I mean, this is a strip which is holomorphic. So if you just make a translation in the real direction, you still get a holomorphic strip, and all the conditions are preserved. Okay. So what is the definition here? Well, now the Floer homology of L1 and L2 is just the cohomology of this complex L1 and L2 delta. And of course, you could say, well, delta may depend on J, or it may depend on, well, in this case, it could only depend on J a priori. But in fact, it doesn't. And what is, of course, non-trivial, as usual, is that delta square equals 0. So otherwise, there's not even a definition here. So let me just, in the last 10 minutes, explain you two things. One is that there's a refined version of this. By what's called the action filtration. Well, the action filtration means that you're going to assign a value to each of the point x and the point y and so on. And that this operator delta is going to decrease the action. So what's easy to define is A of x and y, which should be A of y minus A of x, except that there's again, some normalization by a constant. So how I'm going to define this? Well, let me fix a path from maybe it's simpler if I just fix as a path this one here. So the constant path at x. And now, if I have a point y, another intersection point, I just take a strip like this. I just take any strip. I don't ask that it's holomorphic or anything. And I integrate omega over this strip. So take a strip U from R to O1 to T star n, which satisfies the same properties as here. So U of F0 is in L1, U of S1 is in L2. Well, maybe I want, instead of, if I take a non-compact space, you're going to have the impression that this quantity may be infinite. But it's not the case. So U of S0 is in L1, U of S1 is in L2, and then U of 0 t is equal to x, and U of 1t is equal to y. So consider now a strip like this, but instead of considering this as an infinite strip, which was forced by the fact that I imposed a d-bar equation, okay, you can just renormalize. Okay, it's just homeomorphic to a finite strip. Okay, so I just consider a square, okay, such that one boundary goes here, the other boundary goes here, and then the sides are just crushed here. And what I claim is that this is defined as the integral of the symplectic form over 0, 1 squared. And the fact that the manifold is exact this implies that A of y minus A of x only depends on x and y, and not on the choice of the square. Okay. That's easy to check. It's essentially Stokes' formula. And the other thing you see is that if you take this map U to be up to a renormalization, this trajectory from x to y, if it exists, then this quantity, of course, is going to be strictly positive because you're integrating the symplectic form over a holomorphic object. So if delta of Ex, Ey is not 0, then this implies that A of y is greater than A of x. So I hope I'm going the right, let's see if I'm going the right direction. Yes, x is less than y. So what does it mean? I have this function A. With the points here, which corresponds to the intersection points. So here I have x, here I have y, and here I have z, and so on. And I know that this, maybe I should like this. I know that this coboundary map, this delta map, can only go like this. Only goes up. And this is exactly like the gradient flow of a function. If you're looking at the gradient flow of a function, it always goes up. And it's going to connect critical points at lower levels to critical points at higher level. I mean, you're going to have trajectories. And this is exactly what we're doing here. You could actually define this action not only for this constant path here, but just for any path connecting L1 to L2. You can compute the value of A by just the same trick, using a square with boundary on this trajectory here. And you would get the function on the set of paths from L1 to L2. And this expression here counts some kind of formal trajectories. So at that point, it's just on the formal level, but formal trajectories, gradient trajectory of this function. So it's exactly like on this picture here, you have a function, and these are gradient trajectories. And formally, this is exactly what Floer homology is doing. So because it's in this, it has this property, you can consider a subcomplex of the. So you can consider FC star, let's say, between A and B, which is the sum of K Ex, where now X not only belongs to the intersection of L1 and L2, but moreover, the action of X belongs to the interval AB. Now, as I said, this is not completely well defined because there's always a shift by a constant. I have to choose at some point a normalization. So A is only defined up to a constant, but let's say in some way you choose this constant, and now you sort of stick to it. Okay. And now if the good thing is that the coboundary map is going to send, FC star of, so here I have, let's say, A infinity from FC star of A plus infinity. Of course, here of L1 and L2, always. So if I'm only looking at the points which are above a certain level in this picture, I know that the coboundary is going to send you to a higher level anyway. So it's going to preserve things. And so you can also do quotients, and so you get the Floer homology between, let's say, A and plus infinity of L1 and L2, or by going to quotient, the Floer homology between level A and B of L1 and L2. And now the nice thing, which connects with the previous result, is that the Floer homology between A and B of L and the zero section is the same as the cohomology of SB and SA, where S generating function quadratic at infinity for L. So the connection between, you see you have actually the same indeterminacy on the function S and on the function A. Okay. S, I told you, is only defined up to shift by a constant. A is also defined by shift by a constant. And you can in some way arrange that this shift by a constant is the same or compatible, so that you have this property that for all A and B, the relative cohomology of SB and SA is the same as the Floer homology between L and the zero section. And I think it's just time to stop. Thank you for your attention.